Hi everyone. Um, Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. Today we're going to be continuing our discussion of the Lisp interface library, which we've been covering for the past couple of weeks. The last few weeks we've mainly covered kind of the basic design theory and metrics that the Lisp interface library kind of encompasses. Some of which were related to some of the built-in structures that are already available in the library, as well as a basic principle of how to leverage the library when you are using it for your own application development. So to recap just very quickly, as mentioned multiple times, the Lisp interface library provides a series of uh, data structures as well as algorithms and library functions that revolve around this principle called the interface passing style that was devised by the author. Now, here inside the Lisp interface library, as we've been discussing the last few weeks, we've talked about the fact that the interfaces themselves are first-class objects and may be dispatched on, and in fact, it's a key feature of the system where you pass in the particular interface that you want an algorithm to adhere to and the data structure that or object that you are trying to dispatch on as well. And the underlying cross machinery will take that interface object and the objects that you're passing in as arguments, look up for the particular function, and dispatch on that. Now, we looked at this particular example here last week on how one might, for example, start with a simple generic algorithm like the lookup algorithm that's available in Lil interface all, pass in their interface object as well, and provide um, some data associated with that we want to actually operate on, and the rest of the arguments that the object needs. And the underlying machine will look up and make sure that the second argument, the object that we're adhering on, will more or less is an invariant of the actual interface itself. And if it is, it will go ahead and then run through the algorithm itself. Now, there's not a lot of magic here that's happening behind the scenes, but one of the advantages of this design is now if we go ahead and decide that we may want to switch over to, say, using a different map structure or a different even a different structure that's behavior is slightly different. So instead of using a pure style, we might want to go with a stateful style. And by pure, I mean functional. We can go ahead and do so, and we don't have to actually change a lot of the code that we're dispatching on, that we're actually calling on. As long as we stay and adhere to the generic interface at the top level, we're just merely changing the actual interface potentially, as well as the data that we're passing in. This shouldn't be, anybody who's familiar with the common Lisp object system and folk coming in from other language, this shouldn't look entirely foreign. It looks very much like your basic changing of arguments and implementations, kind of in an interface-centric way, whereas in more traditional object-oriented languages that are not, Smalltalk inspired or that look more like Simula, the interface actually requires you to maybe construct the object ahead of time and then upcast it to the interface before you call the generic methods on, and then internally the compiler will use the generated lookup tables that it created at compile time to figure out which subclass to actually call on and which interface to actually call on. Okay. So a couple things that I want to also mention here. A lot of the built-in libraries that are built-in like packages, that the Lisp interface library provides revolve around this particular design, and it's a key portion of the design. But in the documentation, he mentions that There might be there are other ways where you might want to leverage interfaces, particularly you may want to make them implicit, whereas the API will look very Lisp-like in that it might be just a function call taking in arguments, your standard uh, required key or optional arguments, and internally it will then call the appropriate or set up the appropriate contract with the interfaces before it actually runs through the algorithm. Now we'll touch base on this a little bit, but I want to mention that although a lot of the core uh, functions in the Lisp interface library more or less explicitly spells out what you need to pass in, where the first argument is certainly the interface that you're dispatching on. If you're trying to make kind of a function-centric API, for example, versus maybe something a bit more object-oriented, and you could certainly do that by setting up your interfaces with the appropriate overloads, and then you can then create another layer on top of that where it's just a function call that would ultimately delegate to that method that you defined earlier, and then you can go ahead and dispatch on that. This way you're hiding the complexity of using some of the interfaces directly and knowing which interfaces that you're passing from the actual consumers of your API. And we'll see an example of that later on, but I thought I'd at least briefly mention it here since it kind of closes the final pieces that we touched base in the last few weeks. The Lisp interface library has a series of data structures already available at your disposal, one of which we've already seen, mainly the number map as well as the string map, both of which are concrete interfaces that allow you to essentially look inside of an AVL tree where the key is a number or a string for that matter, and it has an implicit ordering that is based on, I think, string equals or EQ, the equals ordering inside with respect to numbers that has defined by Common Lisp. But in addition to that, there's another A-list data structure that I wanted to mention, and that is the hash table interface. The hash table interface allows you to essentially implement, so it internally has a hashing function that you can certainly use with the same associative lookup as all the associative lists that we've been looking thus far. But internally, what it does is it takes your information and it will take a default hash function and then generate a hash for you. So, as an example, I have a lookup here that uses a hash table. And as you can see, this is very similar to what we had originally in that when we looked at our original example on lookups, we had something like this where we are taking a list, okay, and then we just passed in a series of name value pairs. In fact, let me go ahead and do this. Just copy this one, okay, and then we just went ahead and we looked up the year on this, and we saw when we compiled this, we get 2021, which is what we were looking at. We're looking for the value of the year. Here, notice we're doing the exact same thing, except we just simply did two slight changes, one of which was we changed the, as before, when you're changing interfaces, you have to do this. We changed the interface that we're dispatching on from A-list to hash table, and additionally, we're calling the A-list to map converter that's available in the little to actually convert an A list into a hash table based on the interface that we passed in as a second argument here. So this actually allows us to go ahead and get the same result that we had last time too. Now, what exactly is this implemented as? Well, the hash table inside the lil is basically an AVL tree node, whereas the key is based on the hashing function that you provided. And of course, you could change if you wanted to do a different hash function. You can certainly do so. By default, it is using the built-in SX hash that's available in Common Lisp that will take in any argument that you provide and will go ahead and generate a 64-bit hash for you. Actually, I think it's 61 bits because of the tag bits that are being used. Now, you can certainly change this to use a different hashing function, maybe even a cryptographic hash. That's not available as part of the core library, as far as I can tell, but it's certainly nice that there is already a basic hash table in here. Now, when I say that this is an AVL tree node, it is implemented basically like most standard hash tables that are available in a lot of libraries. Specifically, they are using a bucket map and load factor to actually consolidate a lot of multiple entries, especially in the cases of collisions, and it's written in a chain-like style, so you still might end up getting a indirect lookup cost because it's not actually open addressing where it tries to populate and re-expand the hash table when it's filling up. If you need some of that, I'd encourage you to implement your own hash table because a lot of the ones that are available essentially do this kind of design in particular so that it still is amortized constant, but it's not actually worst case constant because of the fact that it's using still a tree-like data structure internally. There are other ones that are available in terms of the data structures. I'm just going to briefly mention a few of them. A lot of the ones that you may have been hearing me talk about are specifically associated with the A-list interface. That's mainly because we've been playing, well, a couple of reasons. One, we've been playing around with it quite a bit during this discussion, but additionally, from what I've read, of all the stuff that's available in the library, the most complete is actually the key value pairs things because obviously there are some advantages of having your own hash table implementation, especially if you do it correctly, and if you have a couple of things that are, correctly associated with it. So today we're going to probably just doing some live coding here, just to explore some of these libraries before I get into the second topic, which is how to create your own concrete interfaces. But to give you an example of some of the stuff that's available, we could just merely look at pure map, for example. Now, one thing to note about how this library is kind of structured, there are, and I think I've mentioned this before, there are two sides to this. There are pure functional data structures that are available inside the Lisp interface library, as well as what he calls stateful data structures, which kind of try to optimize for quick access and mutation. Obviously, folks coming in from languages such as C++, seeing this kind of split, especially when it comes to writing generic algorithms, isn't very new because of the fact that in those languages where, especially if you have generics such that you could write extremely generic functions, there's a way for you to then dispatch on a purely functional version of the data structure as well as a stateful version of the data structure without actually changing the algorithm itself. as long as the underlying algorithm implements some interface methods that are common to both the pure side and the stateful side. But it's very useful, especially when you're reading code, to know if something is pure or stateful, because then there are some assumptions that you could certainly make and work around as you are working through the code itself. Now, a lot of the pure map and even pure A-list, as we saw before, had quite a few generic functions. And we're going to just touch base on some of the generic functions that are available here. We only looked at the lookup now, but there's also another one that's kind of like the basic iterator class, and that is for each. But I will actually do instead, let us do, let's try for each for right now. So for each will require you to pass in an implementation of the for each iterator. Now, the first thing you may notice is, can you pass in sub-interfaces of this? Well, yes, you can actually pass in any interface that essentially is a sub-interface of for each, which brings up essentially another design principle, which I think I've mentioned, but go ahead and correct me if I haven't, and that is the fact that interfaces are compositional in the Lisp interface library, just like in other libraries that implement kind of some form of parametric polymorphism. And in fact, it is using that compositionality to actually implement the parametric polymorphism inside of the library, which is kind of interesting to actually take a look at. So let me just pull this up just 1 second. Let's see here. Let's pull up. So one way of actually figuring out a library to see if so one thing we need to first do is we need to figure out what kind of implements this guy. So easy to do that in Sly. You could just do mh. Let's see here. Where is I guess that can only occur in my editor. We could just go ahead and see what implements mhs, the specialization. We have two types of specializations. We have collect, collector. Let me see something here. This is just taking in the for each. Nope, that's not what I wanted. Actually, that's not what I want either. Let's see here. MHR. Who references it? Okay, linearizing map and then mutating map is what implements it. So let's try linearized map. Let's see if that actually will do what we want. So what the for each function should do, let's see. Actually, you know what? Let me do number iterator, because I'm thinking that this guy actually implements this. 1, see. Number iterator, class precedence list. We have iterator slot. That does not look like what I need because I should actually pass in. I'm pretty sure if I just do this, all right. We do go ahead and look at this implementation. Let's do actually map. I don't think is what I wanted. Map actually does implement though. No, that's not it. Let's go here. Move this out. Go into interface, iterator, Lisp. Sorry, for some reason this occasionally happens when I'm using do me max and I'm switching between buffers. Let's see here. So we have iterator implementing iterator stuff. Make number iterator from the style of loop. Let's see, for each is type. Ah, excellent. I could just pass in an iterator and it should work. Okay, let's try that. Let me split the window. Let me switch back to my tutorial. And let's see here. Let's see if this works. So we do lil interface iterator make number iterator. Okay, from zero to 10 by 2. Let's see what happens when I do this. It will return, requires at least 3 arguments, right? Sorry, must have done something. And the function f. Let's go ahead and make a function and just square it. Okay. And we compile this. See this. There is no applicable method with arguments, blah, 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 increasing number iterator. Okay, so this is kind of illustrating one thing that I've noticed that I think we should first discuss before I really start debugging into this, and that is how does the interface dispatching all work? I talked about this a little bit last time when we were talking about A-list itself, but I think the easiest way to illustrate it is through an example. I actually written an example here, and then we can get back to this. Unfortunately, the for each example that I'm trying to write kind of touches base on this, so I have to cover this first. I'm realizing. So, as mentioned before, interfaces in the Lisp interface library go into either abstract mode or in concrete mode. Okay, abstract interfaces are interfaces as just like any other languages that implement interfaces, or interfaces that cannot be instantiated, more or less. They're not objects in their true right. In fact, some languages know that if you attempt to try and instantiate an interface because of the interface keyword, it will throw a compiler error telling you that this is not an abstract class or an interface class. So, and in fact, in Java, for example, there's interfaces, and then there are things called pure abstract classes, where if you have abstract methods inside of a class, you cannot instantiate the class itself. Same thing with in C++ for folks who are familiar with how interfaces work in C++. C++, a interface in C++ is basically a class with pure virtual methods. Now, if you have even a class with one pure virtual method, it's automatically considered a pure abstract class in the sense that it cannot be instantiated. It's requiring all its subclasses to actually implement all the methods associated with it. With respect to the actual library that we're discussing, this is kind of the same thing. So the abstract interfaces themselves are more or less the top-level root interface that defines the operations upon which the type families should define. And if you try and actually create an instance of this interface, because again, this is just a class in terms of the common Lisp object system, if you try to do a make instance or what have you, it's going to throw an error because of the fact that the underlying machinery will recognize that it has an abstract keyword and it'll throw up an error. So in order for us to get around that, you need to actually go and implement a concrete version of that interface. So as an example of this, I went ahead and took the simplest interface that's available inside the Lisp interface library and decided to go ahead and show you an example on how one might actually go in and implement one of these concrete interfaces. Now, this is just a simple thing called emptyable. All right, very simple function and very simple interface. Let me go ahead and pull up the actual definition so you guys can see this. Go ahead and do this. Oh, sorry. Okay. So there is actually an instance of empty object. I didn't have to create that myself. All right. Emptyable. Okay. So emptyable is the top-level interface object that's an abstract interface that holds two generic functions. Okay. One, whether or not something is empty. All right. It will return a empty object of the emptyable type. And it also implements MTP, which is a predicate to determine whether or not a particular object is empty. All right. Now, I went ahead and, although empty object is available in this class, I went ahead and recreated this just to show you guys a simple example of how all this works. But let me go back to the tutorial. One second, I think I may have accidentally. Okay. So in this case, what I did was I created an empty version of this interface. Okay. Now the only difference between this concrete interface and the abstract interface that you saw earlier is if you can see this. Let me just do this. Okay. Is the only difference between these two interfaces is the following. If we put this as side by side, is one is labeled as abstract, all right, and the other one is not. Okay. Now, this is easily seen, the fact that when you do define interface, again, just to reiterate this, it's the name of the interface itself, first argument, super interfaces, and then the list of slots to make it parametric, as you can see here in line 12, and as well as line 73. So after that, everything else is an option. The fact that this didn't provide any additional methods or any additional generic function declarations, this is a concrete interface that we can now leverage, right? But we're not completely done yet, all right? We have to also define a set of methods that essentially tells class that this interface exists and it should be able to be dispatched on these particular objects. So we need to essentially implement these generic methods that are defined in the actual abstract interface itself. How do we do that? This is kind of normal class machinery. First, we create, a class here to represent empty objects, which, by the way, is already available to you. Although I don't believe yeah, it is. It's available to you using little interface empty. And then you can just go ahead and implement the methods as is. You just, again, specialize on the concrete interface as the first argument, as I'm doing here. And then the rest of the arguments in the function signature, you could, it's just, like standard class machinery. You could specialize on those particular objects generically or more specifically, depending upon what you want to do. So an example of this that I noticed, at least when I was implementing this myself, is let's say that we wanted to create, just a pure implementation for all the different types of empty objects, right? Well, there's two cases. One, anything that is subclass of type T, all right? You want to say that if this is an instance of type T, then obviously it will be nil. And then let's say that is an empty object itself that you created, maybe with a constructor that you created, like a defun make empty object that simply calls make instance on empty object, so we could get an object instance of that, and we have these already available. We would probably say, okay, we've created an empty object. This is obviously empty. But what about some additional cases, like say null objects or vectors, right? Obviously, for null objects, and what I mean by null objects, it's basically if you use type null here, or if you have an object that is defined as null. So if you define that as a parameter and you set that to nil itself, that's going to be also a type of null. And you can see this by just doing type of this guy, and you'll see that it's a null object. You want to have an override on that too, so you'd want to put specializations for that too as well. But the entire time, the actual interface itself, the actual signature, has not changed. The first object is always going to be the empty object interface. Everything else is just a specialization that you're trying to essentially specialize. This is a built-in feature of the common Lisp object system that we've just seen, that we all love, that this library just essentially layered on this additional piece. So he's like, well, since I have this ability to actually dispatch any way I feel like with the specializations that are available already in Common Lisp, I could just certainly make just the first argument hard-coded to some interface check that I can do, and as long as these specializations exist, I can just go ahead and dispatch on it. So this example here kind of shows you that you're still, at the end of the day, although you're defining these concrete interfaces in these generic functions, you are still also only dispatching using your standard method combinations. which I thought was pretty neat. It basically extended standard method combination essentially to allow you to write far more generic functions, particularly functions that adhere to a specific set of methods that could be checked at compile time if you really wanted to using check invariant, which is pretty useful. Any questions? Okay, so based on this, we can go back to what we were checking up. We need to essentially figure out the concrete interface of this. We'll start about first checking out this, which is, let me first, hold on, bring this up. Okay, do this. See what happens here. So this is an increasing iterator. We'll stop at 12 because it's inclusive. That's kind of how loop works. Okay. Let me see here if I could do pure linearized map colon interface. Let's see if I could do. Let me think about this for a second. This is going to be an AVLT node. Let's see. Let me see if I could use hash table here. No. Let's do a list. See what happens there. It's not of type. Oh, right, dummy. I still need to use. Maybe I should just use number iterator. Warning condition. Okay, number iterator is. Let's see. Let me see if I do. I use for each the function, the command, it says that it's a generic function, right? That's right. So if I do increasing number iterator, that's also an abstract interface. Okay. Give me a second. Gotta find the subclasses that actually implement this guy. HS. Give me B. Okay. These are all the functions that actually define it, but that's not what I want. I want. Oops. I want. Okay. Let me see here. Hyperspec lookup. No, not describe symbols. Who calls? Let me see what this does. Found for each. No, that's not what I want. Let me go back to. Let me do an apropos on this guy again. Actually, not an apropos. Let's go ahead and describe this symbol. Okay. Oh, it's disassembly. Sorry, wrong thing. It is H, not D. There we go. specialized symbol, class precedence list, direct subclasses is a foldable. Let's do this one. Foldable. Subclasses have divide list, fold left, fold from, but no slots, no data structures. Let me look at the actual there's also a collections class, if I remember, but I think those are just a list of all. Let's see here. So what I'm looking for is essentially a concrete implementation of the foldable class, which I don't think I could just pass in here, because I think that's also abstract. Oops, sorry. Foldable is do this. It's a interface slash fold. That's what it is. And anytime you see unbound, as we talked about before, it means that more than likely the interface itself is a what's it? An abstract interface. See if I can actually jump to that class. Go to no. Describe who sets hyperlookup. No. Ring up that. Apropos package. Let's see here. Okay, fold left, fold right, model fold. Interesting. This is gonna be. Let's see. Let's see. This is an integration test. This should be. The main reason I'm not, I'm attempting to, instead of implementing my own implementation of foldable, which I could certainly do, I'm trying to show you guys some of the available classes that are here. Give me just 1 second. I'm going to go do a quick look up here. Pull up the Lisp interface library documentation. This. Sheds common Lisp documentation. This. Here we go. Okay. I am now looking at the collection classes. Let's see, interface all. Pure. Let's try Q. Because a Q is a simple queue is probably what I want to go with. Let's see if I can do that. This is available in purequeue. Purequeue simple queue. Let's see. Simple queues unbounded. What? Let's see. What is? Oops. Sorry. Go to purequeue.lisp. Let's do that. Where is simple queue defined? Exported definition. Probably is. So one thing about this library as I've been exploring it is that I noticed that he does a good job in separating interface from implementation. So, but as a result, places where I think code should be, I end up realizing that it's in the implementation file, not in the actual interface definition. So if you're looking at the documentation and the documentation that's currently available in terms of exploring this is the quick reference. And I'm hoping to try to put together some more related to this as I've been playing around with it. They don't show the actual implementation files themselves. They only show the top level queue.lisp or interface.lisp, depending upon which interface you're looking for. Let's see here. Okay, this guy is simple pure queue, has a console. Cars, non-queuing is going to be this. So what I have to create. Okay, so this is a concrete class, but it hasn't been bounded by anything yet, which means I have to go and create the entries. wonder if there's a Lisp version of this, just to make things a little simpler. A list all set. Let's see if set has anything that I can use. This is just set from map, singleton, subset, set from multi-subset. Okay, that won't work. Let's go back to what we had before. Let's try this. Okay, let's try clearing this and do a little pure queue create. Let's say see what's available here. Let me try foldable. Okay. Let's see here. foldable interface for So one of the difficulties as I've been going through this is just trying to figure out what collection classes that are around here. I mean, I've been getting bits and pieces as I've been playing around with more of them. See if I could do hash table just to see if that works. I don't believe it will, but who knows? Left on increasing number iterator. Right. Okay. That's what I thought. Let's see here. So I might be using the top. Let me see if I can do this instead. Interface map for each. I'm generalizing this. This has kind of been my current thing. I start with kind of something fairly specific that I see somewhere in a documentation, and then I go look up and see if there's a generic function in it. Most of the generic functions are defined in the top level all. If it is available, it has an exported definition. Otherwise, it doesn't show up. Let me see if I could do. Hold on. FIFO-Q this time again. No applicable method. Still, it's no applicable method, which means it's still not able to find for each example. Let me see if the pure implementation You know what? Let's try that. For each star, the difference between for each and for each star is pull up the actual interface for let's see this. That's not it. Where is the for each interface again? It was in pure map. Let's do that. And about the thought it was in here. Hold on. Go back to this. Apropos symbol. Collector results. Prototype interface iterator for each. Contains a foldable subclass. And this is a foldable subclass, a type of object. Hold on, go back to for each. This guy is collecting message. Let's see here. Let's see if I could do for each star for just the sake of example. Let's do this. A list. And let's try something like we had before. Let's use so what I'm okay. Now that I have that, let me go and look at one thing, which is a list implementation. It calls the function on the key and value. So let me do essentially a map hash here. here just do, let's do this lambda kv, and what I'm just going to do is do values, and what I'm going to do is I'm just going to double the key and maintain the value. Alright, so I'm just changing the keys. Really dumb, contrived example, but it'll illustrate the point. Okay. See if this works. Compiled. Let's see this and that. Interesting. It did not return, but I thought it would return. Let me do this. Instead of that, do return a dotted pair instead. We're doing values. Shift G, still K and V are never used. What do you mean K and V are never used? Oh, got it. Sorry, we should use cons really here instead of the dot. Still says for each all. It will not give me a value. Interesting. Let me go and do this instead then. Let me see if we're actually going to print out. Format key a value a. Oops, forgot to put in the first argument. This guy. There we go. So this is just nothing more than a simple, for each example that uses the A-list. And again, if we switch this, this is going to be the same as before. This is going to change into a hash table or into a map. There are other collections, but unfortunately, for some reasons, as you can see, it's been somewhat of a journey to figure out what data structures are available as I've been going through this. I still need to figure out a couple of them just to understand that. I spent some time mostly to try and see how this all worked, this dispatching stuff worked. So that took that was a bit of a detour. My apologies for folks watching. I hope you can see that there's still quite a bit of undocumented stuff here that I'm just kind of like going through and trying to see what's available and what's not. But I think in terms of the actual design of it, it's pretty straightforward once you know what's available. It's just been a little bit of just of an exploration as we go through it. So let's actually see something here. So let me pull up the directory structure of this guy, because we've been playing around with this, but we haven't actually seen the directory structure of this, and I think it's important to go through it. So the top-level project for the Lisp interface library is kind of split into 5 main packages: core, interface, pure, stateful, and then transform. Core is kind of some of the base functionality in the library. It contains mainly the top-level interface class. You may not ever touch this, but this is, if you're ever interested, it allows you to This is kind of the base of where all algorithm design will end up falling. So when you create an abstract interface of your own, you're actually going to essentially implement it as of type interface. Now, it may not be specifically interface, it may end up being like type, as you saw in some of the examples that we saw earlier. But it is something to be aware of, that this is kind of the same hierarchy that you would normally see if you used Common Lisp object system, whereas instead of interface, it would be T. The interface section contains several main interfaces, one of which is this is for your boxing types, and boxable types are basically, in many languages, especially if you talk about serialization, or if you're talking about object referencing a primitive type, and I'll use Java as an example in here. There is primitive types, and then there are boxed version of those primitive types. And what a boxed version is an object that internally holds a reference to that primitive type. So this way, that object can be, in that ecosystem, it can be moved around, it can be garbage collected, it can be whatever. Box types are basically that. They allow you to essentially hook into the existing machinery of a system, and allows you to essentially reference that has a normal object reference type versus an actual value type in many cases. So this is just a set of normal things that someone may want to use if they want to create, boxable types. The other thing that I wanted to kind of bring up in here is and I thought that I was using this right when I was trying to go through that example earlier, is the collection. So if you have, say, let me go ahead and increase the size here. You have different types of collections. Again, when you're trying to create some of this stuff, you would have, say, a finite collection, a global collection. There are you can actually go in the command line and make instances of these interfaces if you really wanted to, by just doing this. And you will do little interface collection, finite collection. But obviously, finite collection is an abstract collection, as we see in here. And the finite collection is usually overridden to implement different types of finite collections. So I could certainly, for example, implement, that might be something useful to do. Although this might be a fairly large collection to actually go and implement, but we can go through that. That'll be an interesting example to go through. Let me see. There's even a smaller version of this. Encoded key collection. Finite collection is probably the top level one that I need to do. Shadowed in pure and stateful. Okay. If it's shadowed, let's go to the pure version. Lisp. There's the finite collection, and it's emptyable. Notice one thing for folks who see this: Common Lisp doesn't discourage the use of special characters inside your interfaces, and it allows certain kind of nice affordances. If you remember from Don Norman's design of everyday things, affordances are good ways of indicating the intent of a particular functionality inside of a product. In terms of APIs, especially APIs in Common Lisp or even Scheme, using something like the bang, which is normally typically in Scheme, recognizing that this is a non-modifiable operation, it's an immutable operation, they'll create a new thing, will indicate to the programmer that this set of functions is going to be creating new instances of a particular thing, and it helps go through that. So this is a particularly large function, but I think we can go through an example of this. Let's see. I was hoping that there was already some predefined stuff in here. Let me check something. Okay, it doesn't look like they predefined any of that. Shoot. I was hoping I didn't have to go through this, but that's okay. Let's see. Queue implementation. Let's try this one. Let's go back to sequence, see if sequence has anything. Sequence is a financial. Oh, it hasn't been implemented yet. Good. All right. Let me see. This interface sequence.lisp. Alright, so he didn't implement that either. Let's see the implementation. Okay. I was hoping that he had a sequence implementation already available, but it doesn't look like it. So it looks like we're going to have to write our own. Okay, it's going to be a good exercise for folks. Sorry, this is turning out to be. I mean, this is our live coding session of the program. I've been debugging a couple of things for those just joining in us right now on the live stream. There's a couple of things related to the actual collections of what's available and what's not available that I've just been hankering on. Let's see if I can go ahead and implement. So sequences doesn't look like it's available, but that will be okay. I think I can actually go and implement that. Let's go ahead and create a finite sequence class interface in our tutorial. All right. So this is going to be an illustration on how to hook into the rest of these algorithms. Now, this, as you saw with empty already, a lot of the design metrics of it is create your abstract interface, and before you do so, check to see if there's if the interface has already been defined inside of the library, like I just did. We're going to create a concrete version of this so that it can be instantiated mainly by the Lisp machinery, and then we can go ahead and see how might what's it? We need to define the methods that actually implement that interface. So then that really hooks it into the machinery, and then we can actually leverage the algorithms when we instantiate them. All right. So to do this, and honestly, this is going to be my first time going through this, so I'm going to be making mistakes as along the way. Folks watching who have corrections, please let me know. I'll go ahead and make these things, but this is all going to be live. And, you know, one of the risks of doing live coding is making mistakes. All right, so let's go to it. I know we're going to be going over today a little bit, so those who are able to stay on, I appreciate it. Those who can't, I just want to take a brief moment to say thanks for joining into with us. Before I continue this live coding session, I want to also bring up a couple of announcements for folks. Tomorrow at 11:30, we will be having a bit of a test run on a new study group that we're starting for Atlanta Functional Programming, the Haskell study group. We're going to start covering the Haskell programming language and its ecosystem. Join us if you're available. We will be covering the same material next week again on the 18th, just to begin our actual study group. We're going to begin next Sunday on talking about the lambda calculus. Tomorrow is more of a lightweight discussion. We're going to probably go through the same presentation. Our very own Judd Taylor is going to be doing the presentation on the lambda calculus this week and next week, and we will start having that on Sundays from 1:30 to 3 Eastern time. I will go ahead and also post, since many of our attendees on the online meetup has also been joining us internationally. I'll try and get the GMT time and post it inside our meetup too as well, because I don't believe if you go on meetup.com that it might provide localization if you're in that particular area about the time that it will actually be scheduled. 1:30 EDT, yes. Just like, so the same time that you see for Common Lisp Study Group, it's going to be on Sundays for Haskell Study Group. I meant 1:30. 1:30 p.m. Atlanta time. And for folks who are again international, I will we'll make a note to actually also post the GMT time on the announcement too as well, so that way you guys can adjust to your time zone and then see if you'd be available to actually join us. All right, let's get back to it. Okay, so the first thing we need to do is we need to go and define a finite interface. I'm going to start a new file here for this guy. And again, I will post all these. You know, it might be useful to do this little tutorial, finite sequence example. I'm going to create a new project, and then I'll post this on. I'll post this all this code on Atlanta FP as a GitHub repository. Let me first do that, which means up until now I've been writing in like a Scratch file, a kind of a tutorial file, but since we're kind of coming up with some more examples, I'm just going to go ahead and create a proper project, so this way folks can just quick load it into their local stuff. Give me a moment. I actually updated my my SBCL narrative recently, so I'm recompiling projects as I stuff as I go along. So okay, as well, local projects, AFP little tutorial. Okay, and depends on, let's do just the Lisp interface library. And I'm going to also say Alexandria. Just whenever I don't need Alexandria, I always end up needing Alexandria. So it's just a standard. Okay, so now let's go ahead and open up our newly minted project. Oops. As well, local projects, APL, source. And actually, let me go ahead and update this guy to increase, have a file, let's call it finite sequence. Now, I'm just going to put in the machinery today. And hopefully come up with examples, but I will not write the tests yet. I think that would be, we'll see if I can get in, if I can get in the basic machinery in so that I can show you that we could get this in. We could start, we should really technically write the tests in first, but I'm not familiar with how to hook that all into Rove right now. I have to see how the existing unit tests that are written in the Lisp interface library kind of like function, and then we can, you know, structure our tests accordingly using Rove instead. So this way we don't have to go and add an additional library just for the sake of unit testing. Okay, so let's go here, source finite sequence .lisp. Okay. First, we need to go ahead and obviously define our package. And I'm going to go ahead and use UIOP define package. Since UIOP is already available, we could certainly do so. Call this afp.lil.tutorial. Folks who think that I should use def package, I started using UIOP define package just because there's some functionality related to hot reloading that I think is pretty neat, that I think you can certainly use to your advantage. I will not, for simplicity's sake, I will not go ahead and add lil directly, just because I know for some folks adding the packages in the use column in the package might be useful. I've just been burned in the past with name conflicts a lot more often than necessary, and as a result, I almost, other than use CL, I almost never use a particular package, just because that way I've completely thrown out any possibility of getting name conflicts, because I'm forcing package usage throughout the use of the package. I know for some folks that might make it a little bit more typing, but for me it at least shows from one standpoint where something is defined. This is just my personal preference, folks watching in. Since I don't have any exported symbols for now, I'm just going to go ahead and not define that, but as we obviously work through this, it might be useful. Okay, so now we're in that. I'm just changing packages in my REPL. Go ahead and change that too. Okay, so the first thing that we're going to do is define an interface. So here, that is, as I mentioned before, is in it's in core define interface. So now we're going to call this finite sequence, and finite sequence is going to inherit from finite collection. Finite collection. For the time being, I'm not going to define any sort of parametric types. So this second list is going to be empty, just because I'm I'm going to only be dealing with numbers right now. Although obviously, if you know that for sure, or if you know that you want in your algorithms that you want, what's it, specific types to have type constraints to be available, especially at the level at the instantiation time, you'd want to actually make this non-empty and make this a parametric interface, not just a normal interface as I'm doing here. But right now, I don't think for simplicity's sake it's necessary. Let's do this now. Now I need to go and recall what the finite collection class actually defines. So let's go ahead and pull up collection.lisp again. Let's do this interface collection.lisp. Yes, it is. Okay, finite collection. So let's see. It looks like finite collection requires that this need to be parametric here based on what I'm looking at in this entry, the list. The key let's see here. If we do that, okay. Certainly appears to be the case that we need to go and define that. Okay, let's do that. I'm not entirely sure why, since it's a sequence class. Collection class is going to be a sequence class, so let's see. Actually, you know what? We could just say key interface arg interface. Let's see. Let's call this guy. This is still going to be a finite collection, but it's not. What we really want is a finite sequence. You know what? Instead of doing collection, let's just go ahead and implement the sequence class the way I think it should be implemented. This way, if this all works, we don't need to do. I just created something that might be useful for the project as a whole. So let's do that. Let's go ahead and implement sequence. Now, sequence, the main thing that you need to think about when you're thinking about sequences, at least with respect to common Lisp sequences, is technically lists. And I can just show this to you. A list can be a heterogeneous list here that could hold different types of values. They don't need to be the same homogeneous type. You can make a homogeneous sequence if you wanted to, but one thing that I will mention is if that's what you want, there are different ways of like actually implementing that. I'm going for the simplest example here. Specifically, that I'm just going to use the built-in heterogeneous sequences for the sake of our example. And I'm just going to implement then on top of that the necessary functions to actually go in and use some of the existing functionality that's available. So interface can, for sequence, it's going to be an abstract interface. Let me just go ahead and do that here. This is an abstract interface. So, and we want these things to be, these sequences to be sizable and copyable and foldable, much like finite collection. But as you can see there, and emptyable for that matter. But as you can see in our earlier example there, unfortunately, actually no, we want sequence, the top level sequence, to be definitely emptyable, copyable, and foldable. Sizable, I don't know if sizable means that it should have a size or if it shouldn't, but I guess since it's emptyable, it's probably going to be the same thing. Let's see. Let's see, sizable. We'll do sizable. We'll do interface all. Foldable. Copyable. And emptyable. Okay. Now I know this already looks similar to. Actually, it's probably better to do it this way. But this looks similar to our finite collection class, as you can see above. But the differences is going to be in the functions that we're going to define on this interface. Isn't a homogeneous list just a vector? I thought. I think you can. I don't know. Hold on one second. So a vector in, so there's a question here. Isn't a homogeneous list a vector? So in Common Lisp, yes, vectors are homogeneous and they're contiguous based. But when we're talking about lists, I'm talking about essentially consoles. So like a linked list essentially. And there is no such thing as a homogeneous list. Well, a list of a single data type in Common Lisp if you're using the list data structure itself. You could make it. It's not actually stressed though. All lists, at least if you're using like list, the list keyword, like I did here in this example here, they are creating essentially consoles that can hold anything. So whereas with a vector, since it is a contiguous block that's allocated at the time that it's constructed, it uses the element type that you could see in when you do make vector or make array. Sorry. In the keyword arguments, when you're specifying the dimensions, you could specify that this element type is of, let's say, in this unsigned byte 64, and you've already made a vector of 64-bit integers. Okay, and you know that this is all, each one of these is the same slot because that's what it's used to behind the scenes to allocate that entire thing. Whereas with the list, each individual console is allocated separately, so it can be anything that's held in there. So that's what I meant by a homogeneous list, not the vector. It's the representation, the data structure representation is what I'm talking about. Although you're right, technically there is a homogeneous sequence type, and that's a vector inside Common Lisp already available. So okay, so let's go back to this. So this is our basic definition. I'm not going to... I don't think I need to provide anything in terms of creation, in terms of actually... I may have to add some things for adding entries into the list. But certainly, if you're using the built-in functions, I don't think it's needed. So we're just going to go with this for now. And the only thing now left, honestly, is implementing concrete methods for finite sequences. All right. So we need to go ahead and make one more technically define interface. Actually, you know what? I'm going to say that. I'm going to go look at sizable for a second, and then I will determine whether or not we need to make a finite sequence or if we can just make the sequence class. Okay, we do not need to have a fixed size anything. So I can actually not make this and instead just make this into a singleton. All right. Okay, definition, trying to instantiate abstract. Okay, 1 second. I have to go and restart my Lisp. I could have uninterned that, but you know, this is probably just the easiest way. All right. Quick load, UFP, little tutorial. All right. So this guy is there. Sorry. Now we're in our little tutorial. Let's go ahead and implement these functions. So the first thing that we need to determine is the size of the objects or the elements in a collection. So one way of doing this is just obviously implementing this for all sequence types. Okay. So when I'm talking about sequence types, I'm talking about common Lisp sequences, which is just listed vectors, and we have a built-in function for that. We have essentially the length of the vector or the length of the sequence. So we're going to just go ahead and leverage that. So we're going to implement first. And again, when you're def mething an existing generic function, we're going to have to go and specify the full signature, which means you need to specify the actual package and then the function name. Now we can go ahead and implement this. Here, our sizable object, I'm just going to call this guy I. Okay. This is going to be implemented using our sequence, all right? And our object is going to be essentially just anything of type sequence. So we need to first figure out, well, what is the top level sequence class, all right? So if I bring 1, 2, 3, you'll see that this is a cons, but if we go and look at the cons, you can see that that's not it. Let me see if I can get, let me try vector instead. Okay. Vector. Need to see type vector. Where is sequence? Sequence. There we go. Okay, so we just need to say that this is of type sequence. So now we've already said anything that's either a vector or let's just go ahead and use this guy. So we could just say now length of the object And that's it. We've just defined our first method on this sequence. Okay. So now this might be a little bit like, well, you already have all this boilerplate now, you're adding this. I was like, once you've implemented this though, the size being universal, you can use any of the generic algorithms that are already available here. So as we go through this, you can see that it'll become clear that this is going to be allowing us to do some other stuff too as well. So let's go ahead and interpret interface size colon size less than or equal to n minus p less than or equal to n. Oh, so this is a predicate that's just checking to see if it's less than some object size. Again, this is going to be our sequence object. Now, folks who are going to ask about earlier, I'm just going to go ahead and clear this one thing up. Yes, it is true that I said that functions can have implicit interfaces and I was going to show you how to leverage that with the with keyword. We didn't have enough time. We haven't had enough time to set up a complete example on here. That's what I'm trying to lead towards. But in a nutshell, when you're defining new interfaces or trying to define the machinery to hook up into the algorithms, unfortunately, you are bound by the fact that you need to use the cost machinery to register it, as far as I can tell. So you can't just necessarily use the with interface on new interfaces unless they have def methods defined on them. Now, if you're using existing interfaces, you may certainly be able to do so, because then it could do some checks with the existing interfaces. Once something's been registered, that is, and has def methods, you could then use it to create higher level algorithms, because those methods have already been defined, and then the dispatching will all work accordingly. If that did not make sense, it'll become clear as I go through this example. So now we have this, it's less than n. All this guy is going to do is just simply do, what's it? It's less than or equal to length of the object and n. Okay, so now we've defined our sizable interface. Let's go ahead and go to the next one, which is what's the next one after foldable? Okay, so foldable is defined in interface/fold. Let's go to foldable. And foldable has a series of functions, okay? And this is starting to get into some of the stuff that a bit more functionality that the library provides with respect to more functional patterns. Specifically, the Lisp interface library implements a series of, I think I've shown this to you, but I don't, but I can reiterate it. I think this requires me to probably do one more talk on on some of the design things, some of the packages, but in a nutshell, let's go back to, let me apropos Lil just for a second here. Okay. So the Lisp interface file library got a lot of its inspiration from existing newer functional languages that are in active use today, particularly Haskell. And in that guise, it actually implemented a lot of Haskell-like Okay, there was a question regarding in my implementation, couldn't I just use size? Yes, I could certainly do so. I could use size. I can certainly replace this and say size object, and this would work too as well. But let me go ahead and do this. I would have to first define that, and then do this. Now this will work because basically everything is bound. But let me go back to what I was saying. So a lot of stuff that is in the Lisp interface library, and a lot of its structure is based on this inspiration from Haskell and functional languages in that family. Specifically, it implements a bunch of monads. As you can see here, there are several already built in. There's transformer monad, identity monad, continuation, and so forth. Maybe, list, and so on. In addition, it also implements a series of functors too as well. I didn't want to touch base on those just yet because I didn't think that we were at a good point to actually go and start going through that, because I think to understand monads in general and functors required to get to this point where we're defining our own interface and start using the library as it's mentioned, as it's defined. In fact, I could say that once we've done this, now, so I don't have to implement all of it. I could just simply show this as the last thing, and then I think the larger discussion of implementing the monadic stuff and the monoidic stuff requires a bit of discussion first to talk about what monoids are, and I think that is a lecture in and of itself. So I'll go ahead and hold off on implementing foldable and copyable for our sequence example for today, just because I know that requires a little bit more theoretical knowledge, that just so that people can understand the terminology and use those concepts coming from those languages in Common Lisp a little bit more effectively. And that obviously needs a little bit more discussion. So let me finish off with the final pieces, which is the two things that we need to implement, which are the pretty simple ones that we've talked about, and that is interface, empty, taking an emptyable, which we've already defined as our sequence object, and what does this function do again? Oh, it's making don't believe I need to define this actually, but actually I don't think I need to define this. Let me see. Little slash interface slash empty. I think I can just simply do that. Oops. Let's say sequence. Okay. Looks like I do need to define it. Okay. What does this function do again? Empty.lisp. It returns an empty, a new one if it's stateful. Okay. Let's see if it needs to be. So let's go ahead and define an empty sequence then. Define L. Oh, actually, I think I could just do a def class empty sequence. subclass sequence. I don't think actually, you know what, that's not going to work, because if I do that, it's going to end up complaining, because in some Lisps, there are no user-defined sequences. So I'm just going to go ahead and define empty sequence like empty object. And actually, you know what? I don't need to do that. I could just simply do this, because it's already been defined for us. Make instance, little interface, actually not little interface, little pure empty. Object. Done. Okay. There's our empty object. Now let's go ahead and define our empty predicate that takes in a sequence, and our object is going to be of type sequence too as well. So what does it mean for a sequence to be empty? Well, really, it's just checking to see if the size is empty. So what we're going to do is just say equals, and then do what we did before, which is call size. Actually, it might be better to just use all the time. Size. In fact, that might be a better idea here too. So whenever you're defining something that's generic, that's already available in the library, it'll be better to actually go in and implement using the top-level all package and see the exported symbols that are available there, just to make it easier. And if you're creating your own extensions, following that pattern makes it much easier for folks to recognize when something is a generic function that can be implemented on any set of types. Essentially, it'll be a functor of sorts. So now let's go ahead and do this, and then say oops. This is it. So now we've defined some of the basic sequences that are associated with this. Let's go ahead and test this out. We will create our we will first check to see the emptiness, which we saw earlier. With sequence, again, good. We will check to see if this, when passed into interface all MTP, and we say sequence emptyable, and you'll see that I forgot to actually define a method for our empty object. Sequence. This is going to be object will pure empty object. Okay, so now we have a true. Let's go ahead and check to see if we call interface all MTP on the sequence on an empty list, what happens? We get a true, we get a nil, and you can see that this will work on both. I'm using the reader macro for both lists and vectors for folks looking in that I didn't. And if I make this non-empty, it's also going to be nil. And dispatching all works. So this will now allow you to then Okay, there's a question here. Does that imply the first definition should replace length? If I understood the question, does size replace length? When you're using the Lisp interface library and dealing with sequences, yes, size replaces length because that hooks into that level, that the set of generic algorithms there that uses size. All right, so when you are using the foldable operations that are built in the Lisp interface library and so forth, although internally it delegates to length, the common Lisp length, this will allow you to then use higher order functions that are already available in the Lisp interface library that uses the size interface size method, and you don't have to rewrite all that code. And 33. So the first definition here, okay, line 15 and 16, that is the only definition that should use length, just because you're kind of telling the interface library how to compute the size of an object, okay? But every subsequent generic algorithm that you're implementing should, especially since you're passing in the interface, it should call upon size, and the top level machinery will then ultimately go and figure out what, using method combination, what actual size method you're actually dispatching on, and it will call it for you. Does that answer your question? Okay, cool. So a lot of this, and I think it should be coming clear that a lot of the decoupling comes from the fact that we're taking advantage of Claus's dispatching mechanism in method combination, okay, to create generic algorithms at the first argument, the first interface argument, and then every subsequent argument will now be an additional specialization just so that it gets a registered function to compute some of the lower level pieces of the library, and then we can use those building blocks to create much higher level generic methods. All right, and this is what also allows us to hide pure interfaces. I mean, pure objects. Those are immutable objects from the stateful ones. Okay, question: what error would be generated if you did make that substitution in the first method? It's going to keep propagating up until it can't find an applicable method, and then it will throw an error saying that there's no applicable method. But we could try that just to see that. Let's say that we did this. Okay. It did not throw any error, but I think until we call something, we won't actually see the error happen. It's going to lock up. Oh, that's even worse. All right, I just locked up. Okay, let's redefine that. Now, if we do this, we're good. All right. It didn't blow up the stack. There is no error. So my understanding on how the dispatching works is ever so slightly off. It keeps going until and probably locks up your REPL instead of actually doing what I thought it would do. Yes, it is very interesting that no error was generated. Comment was made about why there was an error that was generated when you did interface size. I think that's a feature in Common Lisp of not letting the REPL die, even though you did something stupid, and it allows you to do like a software interrupt the repo to go and redefine it if you really needed to. All right. So our building blocks isn't complete. We still have a couple of things to implement, which is mainly copyable and foldable. But I think I'm going to stop here for today, just merely because of the fact that those two interfaces are touching upon a concept that I have not yet discussed, which is some of the more functional-based, Haskell-inspired functional-based concepts that are now built into the Lisp interface library that we need to cover a little bit more in detail before we start defining methods on that and understanding what the implications are from that. So that's it for today. Apologize for such a interesting, it was a long but very interesting journey as we were going through this library. Yes, there was a comment about adding documentation for sequence. Yes, I will certainly do so before I check it in. I will add more comments about what these interfaces are, where they're coming from. Please, those of you who do download this repository and start playing around with it, read through the documentation and provide some feedback, either in the form of pull requests or issues on the GitHub repository, so that way we could kind of work ourselves through creating some of these data structures and so forth inside and use this library and actually make it a bit more complete in terms of, a complete tutorial example for other folks. I really like to take some time to effort, but I'm leaving it up to the viewers, you guys. I can only tell as much as I understand how much documentation makes sense for me, but obviously, unless a third person reads it, you'll never really know. So I'll see you guys next week. Again, we will be continuing our discussion on these two. We're now at a point where we're going to be talking about next week on monoids and functors and applicables with respect to the Lisp interface library itself, as well as we will be talking about some of the what he calls interface transformations, which are things related to how you might want to make something mutatable versus linearized versus there's a couple of other transformers that are available there, and it's related to the Haskell concepts that we're talking about. So appreciate you guys joining me. I'll see you guys next week.